Well, welcome back to our course on software engineering. And we're continuing progressing through the second major section that we're covering. And this is the section on the dependability and security. And so now we've talked about dependable systems, reliability engineering, and today we'll be talking about safety engineering. And so the topics that we'll be focusing on in terms of safety engineering are looking at safety critical systems, looking at safety requirements, considering safety engineering processes and safety cases. So for safety, safety is a property of a system that reflects a system's ability to operate normally or abnormally without danger of causing human injury or death and without damage to the system's environment. It is important to consider software safety, as most devices whose failure is critical now incorporates software-based control systems. So software in a safety critical system, let's talk about that. The system may be software controlled so that the decisions made by the software and subsequent actions are safety critical. Therefore, the software behavior is directly related to the overall safety of the system. Software is extensively used for checking and monitoring other safety critical components in the system. For example, all aircraft engine components are monitored by software looking for early indications of component failures. This software is safety critical because if it fails, other components may fail and cause an accident. So a lot of your pilots doing their pre-flight checkup, this is one of the things that they're looking at. In terms of safety and reliability, these are related, but they're distinct. In general, reliability and availability are necessary, but not sufficient condition for system safety. Reliability is concerned with conformance to a given specification and delivery of service, while safety is concerned with ensuring systems cannot cause damage irrespective of whether or not it conforms to its specification. Systems reliability is essential for safety, but is not enough. And reliable systems can be unsafe. So what about unsafe reliable systems? There may be dormant faults in a system that are undetected for many years and only rarely arises. There could be specification errors. If the system specification is incorrect, then the system can behave as specified, but still cause an accident. Hardware failures, generating spurious inputs can be something that could cause unreliability. And so it's hard to anticipate in the specification. You can have context sensitive commands, for example, issuing the right command at the wrong time. And this often is a result of an operator error. So let's get into safety critical systems. Safety critical systems are systems where it's essential that system operation is always safe. The system should never cause damage to people or the system's environment. And examples are the control and monitoring system in an aircraft, process control systems in chemical factories, and automotive control systems such as braking and engine management systems. For safety criticality, primary safety critical systems, we'll talk about that first. Embedded software systems whose failure can cause the associated hardware to fail and directly threaten people. An example could be an insulin pump control system that does not operate properly. For secondary safety critical systems, these are systems whose failures result in failures in other social technical systems, which can then have safety consequences. For example, the Medcare system is safety critical as failures may lead to inappropriate treatment being prescribed. And infrastructure control systems are also secondary safety critical systems. For hazards, situations or events that can lead to an accident. So examples would be a valve is stuck in a reactor, you have an incorrect computation in software by navigation systems, or failure to detect possible allergy and medication prescribing systems. So hazards do not inevitably result in accidents. Prevention actions may have been taken. It's something you want to be thinking about. So for safety achievement, You can have a hazardous avoidance, hazard detection and removal, and damage limitation. So for hazardous avoidance, the system is designed so the system classes of hazard simply cannot arise. For detection and removal, the system is designed so that hazards are detected and removed before the result is an accident. For damage limitation, the system includes protection features that minimizes the damage that may result from an accident. So here is some of the terminology, and I won't read this, but you're going to have an accident or a mishap. You can have hazard, you can have damage, hazard severity, hazard probability, and risk. So these are all things that need to be concerned about in terms of safety. So for normal accidents in complex systems rarely have a single cause, as these systems are designed to be resilient to a single point of failure. Designing systems so that a single point of failure does not cause an accident is a fundamental principle of safety system design. Almost all accidents are the result of a combination of malfunctions rather than single failures. It is probably the case that anticipating all problem combination, especially in software controlled systems, is impossible. So achieving complete safety is impossible. Accidents are inevitable, unfortunately. So in terms of safety, software safety benefits, although software failures can be safety critical, the use of software control systems contributes to increased system safety. Software monitoring and control allow a wide range of conditions to be monitored and controlled that is possible using electromechanical safety systems. Software control allows safety strategies to be adopted that reduce the amount of time people spend in hazardous environments, and software can detect and correct safety critical operator errors. Let's talk about safety requirements. So the goal of safety requirement engineering is to identify protection requirements and ensure that the system failures do not cause injury or death or environmental damage. Safety requirements may be shall not requirements that they define situation event that should never occur. Functional safety requirements define checking and recovery features that should be included in a system and features that provide protection against system failures and external attacks. Let's now talk about hazard-driven analysis. And there's 4 things: hazard identification, assessment, analysis, and then the safety requirement specification. So in terms of identification, identifying the hazards that may be threatening the system is something that has to be done. The identification may be based on different types of hazard, physical, electrical, biological, service failures, etc. So here are some examples for the insulin pump. You can have an overdose, an underdose. Both of those would be service failures. You can have a power failure, so there's an electrical failure. You can have electrical interference, so the mechanism isn't working properly. You can have poor sensor and actuator contact, so a physical issue. Parts of the machine break off in the body. You can have an infection that is caused by the introduction of the machine. You can have allergic reactions to the materials or insulin from the machine. So in terms of hazard assessment, this is a process is concerned with understanding the likelihood that a risk will arise and the potential consequence if an accident or incident should occur. They can be categorized in terms of intolerable, as low as reasonably practical, or acceptable. And so those are the 3 categories that could be defined and then agreed upon how much you're going to work on for each category. Intolerable, of course, you're going to have to make sure that that is possible. As low as reasonably practical, there may be some things that would be allowable, and then finally the acceptable areas. So here's the risk triangle. So we're reflecting back to those 3 things. And so, of course, you want to be moving towards negligible risks. And so the further you go down this triangle, the better off you're going to be. So what about social acceptability of risk? The acceptability of risk is determined by human, social, and political consideration. In most societies, the boundaries between the regions are pushed upward with time. That is, the society is less willing to accept risk. For example, the cost of cleaning up pollution may be less than the cost of preventing it, but this may not be socially acceptable. In terms of risk assessment, it is a subjective process, and risks are identified as probable or unlikely. This depends on who is making the assessment. So hazard assessment, it is the estimate of the risk probability and the risk severity. It is not normally possible to do this very precisely, so relative values are used, such as unlikely, rare, or very likely, etc. The aim must be to exclude risks that are likely to arise or that have high severity. So here's classifications of the risk for the insulin pump. And so I won't go over this in detail, but you can be looking this over. And so here are the various things that we spoke about before in terms of the ways that you could have a hazard. And here we're giving some characteristics in terms of hazard probability, accident severity, estimated risk, and acceptability. In terms of hazardous analysis, this is concerned with discovering the root cause of risk in a particular system. Techniques have been mostly derived from safety critical systems and can be inductive or deductive. So you can have inductive bottom-up techniques or deductive top-down techniques. So two complementary approaches that can be helpful. You can have a fault tree analysis, and this is a deductive top-down technique. You put the risk or hazard at the root of the tree and identify the system states that could lead to that hazard. Where appropriate, you can link these with and or conditions. The goal should be to minimize the number of single causes of system failure. So here's an example of a software fault tree, and you can see how these are all OR together. And so, and here is the various ways in which they could be coming about from each of these categories. I won't go over this in detail, but this is a fairly interesting chart as you get into the specifics of a particular application. In terms of fault tree analysis, there are three possible conditions that lead to delivery of incorrect doses of insulin. You can have incorrect measurements of blood sugar level, failure of the delivery system, or the dose delivered is given at the wrong time. By analysis of the fault tree, root causes of these hazards are related to software or algorithm error or arithmetic error. There's some possibilities. For risk reduction, the aim of this process is to identify dependability requirements that specify how the risk should be managed and ensure that accidents and incidents do not arise. The risk reduction strategies are hazardous avoidance, hazardous detection and removal, and damage limitation. So for strategy use, normally in critical systems, it's a mix of risk reduction strategies are applied. In a chemical plant control system, the system will include sensor to detect and correct excess pressure in the reactor. However, it will also include an independent protection system that operates a relief valve if dangerously high pressure is detected. So for the software risk in an insulin pump, we mentioned these arithmetic error. So you could have a computation that causes the value of the variable to overflow or underflow. This may include an exception handler for each type of arithmetic error. For algorithmic error, this is to compare the dose to be delivered with previous doses or safe maximum doses. This reduces the potential for having a dose that is too high. So I won't read these, but here are some examples of some safety type of requirements. So that's there for reference. Let's talk about the safety engineering process. So safety engineering processes are based on reliability engineering processes. So they're plan-based approaches with reviews and checks of each stage in the process. The general goal of fault avoidance and fault detection is what we're getting at, and it must also include safety reviews and explicit identification and tracking of hazards. For regulation, regulators may require evidence that safety engineering processes have been used, sorry about that, in system development. For example, the specification of the system that has been developed and recorded of the checks made on that specification. evidence of the verification and validation process that have been carried out, and the results of the system verified and validated. And finally, evidence that the organization developing the system have defined and dependable software process that includes safety assurance reviews. There must also be records that show that these processes have been properly enacted. What about agile methods in safety? Agile methods are not usually used for safety critical system engineering. Extensive process and product documentation is needed for system regulation, and it contradicts the focus in agile methods on the software itself. A detailed safety analysis of a complete system specification is important. This contradicts the interleaved development of a system specification process. Some agile techniques, such as test-driven development, may be used. For safety assurance processes, process assurance involves defining a dependable process and ensuring that the process is followed during the system development. Process assurance focuses on, do we have the right process, and are we doing the process right? Process assurance generates documentation, and agile process therefore are rarely used for critical systems. What about processes for safety assurance? Process assurance is important for safety critical system development. Accidents are rare events, so tests may not find all the problems. Safety requirements are sometimes shall not requirements, so cannot be demonstrated through testing. Safety assurance activities may be included in the software process that records the analyses that have been carried out and the people responsible for these. For safety related process activities, there's the creation of a hazard logging and monitoring system. There's an appointment of project safety engineers who have explicit responsibility for system safety. There can be extensive use of safety reviews, a creation of a safety certification system where the safety of critical components is formally certified. And then there can be the detailed configuration management, which is something we can talk about later. For hazardous analysis, the hazard analysis involves identifying hazards and the root causes. There should be clear traceability from identified hazards through their analysis to the actions taken during the process to ensure that these hazards have been covered, and a hazard log may be used to track hazards throughout the process. So here's just an example of what a hazard log entry could possibly look like. I'm not going to go over this, but you can just see that the various types of information that are provided. And here's just some more information for the hazard log. So it's just some more information that you can review. For safety reviews, it's driven by the hazard register for each identified hazard. The review team should assess the system and judge whether or not the system can cope with that hazard in a safe way. For formal verification, formal methods can be used when a mathematical specification of the system is produced. They are the ultimate static verification technique that may be used at different stages in the development process. A formal specification may be developed and mathematically analyzed for consistency. This may help discover specification errors and omissions. Formal arguments that a program conforms to its mathematical specification may be developed. This is effective in discovering programs and design errors. For arguments for formal methods, an argument could be producing a mathematical specification requires a detailed analysis of requirements, and this is likely to uncover errors. Concurrent systems may be analyzed to discover rare conditions that might lead to deadlock. Testing for such problems is very difficult. And they can detect implementation errors before testing when the program is analyzed alongside its specification. When for arguments against formal methods, required specialization notations that cannot be understood by domain experts. And so can the reference teams that you're bringing in to review, would they be able to do this? It can be very expensive to develop a specification, even more expensive to show that a program meets that specification. Proofs may contain errors, the thing that you're trying to validate, and it may be possible to reach the same level of confidence that the program is more cheaply using other verification and validation techniques. So unfortunately, formal methods cannot guarantee safety. The specification may not reflect the real requirements of system users. Users rarely understand formal notation, so they cannot directly read the formal specification to find errors and omissions. The proof may contain errors, and so program proofs are large and complex. So large and complex programs, they usually contain errors. The proof may make incorrect assumptions about the way that the system is used. If the system is not used as anticipated, then the system's behavior lies outside the scope of the proof. For model checking, this involves creating an extended infinite state model of a system and using a specialized system, checking the mode for errors. The model checker explores all possible paths through the model and checks that a user's specified property is valid for each path. Model checking is particularly valuable for verifying the concurrent systems, which are hard to test. Although a model checking is computationally very expensive, it is now practical to use in the verification of small to medium-sized critical systems. So here's an illustration of what a model checker could look like. You have the requirements in design or program, you build a model, and you are also in parallel having the property specification in the model. You extend the infinite state model of the system, and then you have that feeding into the model checker along with the desired system properties, and you confirm or come up with counterexamples as a result of that. In terms of static program analysis, static analyzers are software tools for source text processing. They parse the program text and try to discover potential erroneous conditions and bring these to the attention of the verification and validation team. They are very effective as an aid to inspections. They are a supplement to, but not a replacement for, inspections. And so here is some fault classes for automated static analysis checks. You can have data faults, you can have control faults, you can have input and output faults, interference faults, and finally storage management faults. And so these are the kind of things that you could be checking for. For levels of static analysis, you can have characteristic error checking, user-defined error checking, and assertion checking. So for characteristic error checking, the static analyzer can check for patterns in the code that are characteristic of errors made by programmers using a particular language. For user-defined error checking, this could be the users of a programming language to define error patterns, these are extending the type of errors that can be detected. This allows specific rules that apply to a program to be checked. And for assertion testing, developers include formal assertions in their program and relationship that must hold. The static analyzer symbolically executes code and highlights potential problems. So in terms of the use of static analysis, this is particularly valuable with language such as C is used, which has weak typing, and hence many errors are undetected by the compiler. This is particularly valuable for security checking. The static analyzer can discover areas of vulnerability such as a buffer overflow or unchecked inputs. Static analysis is now routinely used in the development of many safety and security critical systems. So what about safety cases? For safety and dependability cases, these are structured documents that set out the detailed arguments and evidence that a required level of safety or dependability has been achieved. They are normally required by regulators before a system can be certified for operational use. The regulator's responsibility is to check that a system is as safe or dependable as is practical, and regulators and developers work together and negotiate what needs to be included in a system safety dependability case. For the system safety case, a safety case is a documented body of evidence that provides a convincing and valid argument that a system is adequately safe for a given application in a given environment. Arguments in a safety case can be based on formal proof, design rationale, safety proofs, etc. Process vectors may also be included. A software safety case is usually part of a wider system safety case that takes hardware and operational issues into account. So here is the contents of a software case, safety case. And so you have the description, you have the requirements, you have the hazard and risk analysis that you document, you have the design analysis, and finally you have the verification and validation. All these are included in that safety case. There's also a couple other things. There's the reports that are generated, the team competences that you're talking about what you have. You have quality assurance, you have the change management process, and you have the associated safety cases that you would also know. So for structured arguments, safety cases should be based around structured arguments that present evidence to justify the assertions made in these arguments. The arguments justifies why a claim about system safety and security is justified by the available evidence. So here is just an example of what a structured argument could look like. And you have various evidence that supports an argument. And as a result of those arguments, you can justify a claim that you're trying to assert. So say for insulin pump safety argument, so the arguments are based on claims and evidence, and for an insulin pump safety, you can have a claim the maximum single dose to be delivered will not exceed the max dose. And then you have the couple sources of evidence, safety requirement for the safety arguments for insulin pump, the test data for the insulin pump, and the static analysis report of the insulin pump. So thus the evidence presented demonstrate that the maximum dose of insulin can be computed, and it will ensure that it's always less than the max dose. So structured arguments that demonstrate that a system meets its safety obligation are important that you have. It is not necessarily to demonstrate that the program works as intended. The aim is to simply to demonstrate safety. So it's generally based on a claim hierarchy. Did you start with the leaves of the hierarchy and demonstrate safety? Then this implies that the higher level claims are true. So you enter through the leaves of a tree, if you will. A safety claim hierarchy for the insulin pump, and this is something that you could look through, and we won't go through this in detail for right now. So for software safety arguments, safety arguments are intended to show that the system cannot reach an unsafe state. These are weaker than correctness arguments, which must show that the system code conforms to its specifications. These are generally based on proof by contradiction. In a graphical model, the safety argument may be developed. So for the construction of a safety argument, you want to establish the safe exit conditions for a component or program. And starting from the end of the code, work backwards until you have identified all paths that lead to the exit of the code. You want to assume that the exit condition is false and show that for each path leading to the exit that the assignments made in that path contradict the assumption of an unsafe exit from the component. So here's an insulin dose computation with safety checks, and you can look at that at your leisure. Here's an informal safety argument based on demonstration contradictions. And so you have this logical flow. And this is similar to what we showed a handful of charts ago for a different case. So for the program pass, neither branch of this statements 2 is executed. This only can happen if the current dose is greater than or equal to the minimum dose and less than or equal to the maximum dose. The branch of if statement is executed if the current dose is 0. The else branch of if statements is executed if the current dose equals to the max dose. In all cases, the post conditions contradict the unsafe condition that the dose administered is greater than the max dose. So safety critical systems are systems whose faults can lead to human injury or death. A hazard-driven approach is used to understand the safety requirements for safety critical systems. You identify potential hazards and then decompose these using methods such as fault tree analysis to discover the root causes. You then specify requirements to avoid or recover from these problems. And it's important to have a well-defined certified process for safety critical system developments. This should include the identification and monitoring of potential hazards. And then finishing up with our key points. Static analysis is an approach to verification and validation that examines the source code of a system looking for errors and anomalies. It allows all parts of the program to be checked, not those parts that are executed by a system test. Model checks is a formal approach to static analysis that exhaustively checks all states in the system for potential errors. Safety and dependability cases collect the evidence that demonstrates a system is safe and dependable. Safety cases are required when an external regulator must be certify the system before it is being used. All right, well, thank you very much. That's going to end our lecture for this. Thank you.